Let's now try to analyze. We've seen gradient descent. We have now seen at least one or two methods, momentum-based gradient descent and Nesterov momentum-based gradient descent, which can help you improve gradient descent training. What are the pros and cons of gradient descent that we've seen so far? For every parameter update, gradient descent parses the entire data set. We already saw that it computes the gradients, it keeps aggregating the gradients and then takes the average. Okay, we called it an epoch. So gradient descent passes the entire data set and it's hence called batch gradient descent. And the advantages of batch gradient descent is theoretically speaking, from an optimization standpoint, the conditions of convergence are well understood and many acceleration techniques, there are improvements from an optimization perspective, such as conjugate gradient, operate very well in the batch gradient descent setting. Once again, it's called batch gradient descent because you're waiting for the entire batch of data points to get completed, take all of these gradients, average them, and then make an update. So the disadvantage of batch gradient descent is it can be computationally slow for the same reason, especially if your training data set had say 10,000 data points or 1 million data points, you're going to wait for parsing through all of them before making an update. ImageNet, which is a computer vision challenge, it's a very commonly used data set in vision, has today about 14 million samples, and one iteration over all of those 14 million samples can be very slow to wait for one parameter update. That brings us to a very popular approach known as stochastic gradient descent. Stochastic gradient descent, or SGD, stands for you randomly shuffle your training data set and update your parameters after gradients are computed for each training example. So you randomly shuffle and pick one data point, forward propagate it, compute the error, compute the gradient, update all your parameters right away before propagating your next data point. So here is your algorithmic difference with gradient descent. The third step here, this step 5 here on this algorithm was outside the for loop in gradient descent. You went through every data point, accumulated all your gradients, and then made the parameter update. Whereas in stochastic gradient descent, that step of updating your parameters goes inside the for loop, which means for every data point, you're going to make a parameter update. This is going to be faster. Let's see a few pros and cons for stochastic gradient descent too. But before we go there, we're going to talk about a setting which lies in between, which is known as mini batch stochastic gradient descent. What is mini batch stochastic gradient descent? Mini batch stochastic gradient descent, as the name says, is you take a mini batch of training examples. Don't just take one, don't take all. Take 20 examples from your training data set, forward propagate all of them, compute all the outputs, compute all the errors, compute all the gradients, and then take the average of those 20 gradients alone and update your parameters. Why do we need this? It's possible that if you keep updating your gradient with every sample, it may give you random directions. One data point will tell you go like this. This is where Himalaya's lowest point is there. Another data point will tell you another step. You will just be taking different zigzag steps as you traverse through a surface if you listen to every data point's gradient. Averaging gives you a better sense of a gradient direction that is consistent across a few more data points. This mini batch version of stochastic gradient descent is the default option for training neural networks today. Often today when people say they use SGD, they actually mean mini batch SGD. Remember, mini batch SGD with batch size to be 1 is your SGD itself. But typically people use larger batch sizes, 20, 100, so on and so forth, to compute these gradients. So algorithmically speaking, the applying update once again went out of the loop, but this time you're not going to compute You're not going to aggregate gradients for the entire training data set, but only for one mini batch, which you denote as D mini, and you're only going to aggregate the gradients and average the gradient only for that mini batch in the algorithm. Let's try to see an illustration of stochastic gradient descent. Okay, this is once again a contour plot of an error surface. Let's try to see how stochastic gradient does. You can see it progressing towards the minimum. Remember, the minimum is the blue surface. As it goes closer to the minimum, it seems to oscillate. Do the oscillations remind you of something? Momentum maybe? Momentum also had similar oscillations when it reached the minimum. Here is an illustration of mini batch SGD. Once again, the same error surface. Let's see if batching data points and computing the gradient helped us a little bit. You do see here the oscillations have mildly reduced for mini batch SGD when compared to SGD, but the batch size here was just 2. You could probably see lesser oscillations when you keep increasing the batch size, because then you're not going to vacillate based on every data point's gradient, but you're going to batch them across a larger set of data points before you update your parameters. What are the pros and cons of stochastic gradient descent when you compare it to batch gradient descent? Let's try to understand this. The advantages of stochastic gradient descent, which by far outnumber its disadvantages, it's usually much faster than batch learning when you train neural networks. Why is that so? It's simply because there is a lot of redundancy in batch learning. Because if you have 1 million data points in your data set while training your neural network model, then many of these data points may give you similar information. You probably don't need to wait for all of them to give you the gradient and then average. Even if you take 100 of them, maybe you're going to get some sense of where the gradient is for that particular iteration and move forward in that direction. So you're exploiting the redundancy in data to go much faster than standard batch gradient descent. It also often results in better solutions. This may seem a little counterintuitive, because you would think that by using the entire batch, it could be computationally slow, but that's the ideal way to do it. Then why does stochastic gradient descent yield better solutions? The reason is stochastic gradient descent is a noisy version of gradient descent. What do we mean by that? We mean that you are only taking 20 data points. Let's assume the mini batch size was 20. You're taking just 20 data points, getting the gradient, and you keep moving along those directions. So it's like asking, once again, you're traversing Himalayas. If you ask 1,000 people, assuming that you had infinite computation and infinite access to people, if you ask 1,000 people and they all told you go in a particular direction, you probably can rely on that direction. If you asked only 2 people and asked them what direction to go in, maybe they may get it wrong. Which means that when you ask a smaller set of people, you may oscillate, you may take one direction, then somebody else tells you go in another direction. You keep moving around and fluctuating a little bit, but you eventually get there, because across all of these people, they may point you in the direction. In expectation, you would get there, but there may be fluctuations along the way. But this noisy updates of stochastic gradient descent is what could actually help you in escaping local minima, bad local minima, or saddle points. Because of these noisy updates, you may avoid saddle points and probably get to better local minima over time. That's what researchers have been able to understand from how SGDs perform in deep learning. Stochastic gradient descent is also useful for tracking changes. What do we mean? If you have a new set of data points that come in, it's very easy to update with just 20 data points rather than have to run an entire epoch with 1 million plus 20 data points. Right? So remember, in batch gradient descent, you have to recompute the gradient for all the data points before you make your next move. But in stochastic gradient descent, if new data points come, that's what we mean by tracking changes here, you can easily update the system and keep moving. What about disadvantages? Disadvantages of stochastic gradient descent is that the noise in stochastic gradient weight updates can lead to no convergence. To this day, sometimes, remember as we said that because of the complexity of the error surface, where you initialize your weights is very important as to which local minima you converge to. So often today in practice, if in the first few iterations you find too much fluctuations in your error, people often simply change the initialization and try again. Which means noise in SGD weight updates can lead to no convergence, but the solution is fairly simple. If in the first few iterations things are not going well for you, just stop. Go back and start at a different location and start all over again. It's fairly a simple solution. This can also be controlled using learning rate. If the gradient you know is noisy, don't use a high learning rate. Okay? So it can also be controlled using a learning rate, but then identifying a proper learning rate can be a problem of its own. And that's the problem we're going to talk about next. How do you choose a learning rate? Okay. We said that momentum was one way to artificially inject a learning rate into the system, right? Because it's effectively, if the momentum, the previous step and the current gradient aligned, it's almost like you had a high learning rate in those directions. In general though, if learning rate is too small, it can take a long time to converge. If the learning rate is too large, the gradients can explode. Now, how do you choose a learning rate in practice? Assuming we don't use momentum, how do you choose a learning rate in practice? One simple option is naive linear search. You just keep your learning rate to be constant throughout the process. Just fix it. Just use the same learning rate across all your iterations until you reach convergence. Or you could use annealing based methods. Annealing based methods are methods where you gradually reduce the learning rate over time using some formula that you come up with. Okay, let's see a couple of them now. One of them is known as step decay, where you reduce the learning rate after every n iterations, or if certain degenerative conditions are met. For example, if the current error is more than the previous error, which should not happen when you do gradient descent, you expect that the current error should always be lesser than the previous error. But when you do stochastic gradient descent, that may not be guaranteed because you're using only 20 data points to decide your gradient. So what you can do is keep reducing your learning rate after every n iterations. So that's one simple approach. The idea here is that as you keep training over iterations and epochs, you're probably getting closer to your minima. And when you get very close to your minima, you want to take small steps so that you reach your minima and don't overshoot it. That's the reason for reducing the learning rate over time. That's called step decay. Another popular option is known as exponential decay. In exponential decay, you set an initial learning rate called alpha naught, and then alpha is equal to alpha naught to the power minus kt, where alpha naught and k are hyperparameters and t is an iteration number. So you start with the learning rate alpha naught and keep progressively reducing it exponentially in this particular form over every few iterations. Because t is an iteration number here, as the iteration number increases, the learning rate automatically starts falling down. You can also use a simple 1 by t decay formula where you start with an alpha naught and alpha at a particular time step can be given by alpha naught by 1 plus kt, where alpha and k are hyperparameters and t is an iteration number. All of these, as you can see, are heuristics. We're just saying, let's just do one of these and maybe it will work. Can we do something better? Can we be more aware of what a neural network is doing and accordingly choose a learning rate rather than have these global rules that we fix irrespective of what the network is doing? Is there a way to do this? Yes, there are a few methods which we're going to discuss now. One of the earliest methods in this context was known as adaptive gradient or adagram. Adagram has a simple intuition as to the fact that sparse but important features may often have small gradients when compared to others, and learning could be slow in that direction. In our case, features means dimensions of weights, rather a subset of weights. So you have your entire space of weights, a subset of weights which change only once a while. So let's assume that there are certain weights that do not change with every mini batch in mini batch SGD, but change only once a while. They may change by a small amount, but that amount is important because they only change once in a while. Sparse features could be important, and learning could be slow in this direction because the gradients could be small in that direction. So a simple thought then is, why should the learning rate be the same for every gradient in your neural network? Once again, remember that the gradient is a vector of the derivatives of the loss with respect to every weight in your neural network. Why should you use the same learning rate for all of them? Why cannot you use a different learning rate for each of these weights? So what you do in undergrad is you accumulate the squared gradients as a running sum. RT is a quantity that holds a running sum of squared gradients. Once again, keep in mind that the gradient is in delta theta t is simply the gradient, that's the parameter update, and that's a vector of the gradient with respect to every weight in the neural network. So for each of those weights, you maintain a running sum of the gradient squares, and then your parameter update states theta t plus 1 is going to be theta t minus alpha, which is your learning rate, divided by delta plus root RT delta theta t. Delta theta t is your gradient in your current time step. Now, why is this? Why does this address this intuition? Delta here is simply used for numerical stability. You just set it to be a value like 10 power minus 6 or 10 power minus 7 so that you don't face a divide by 0 error. In case RT is 0, you don't want a divide by 0 error when you compute. So that's the reason you have a delta there. But otherwise, what this is doing is when RT is small, which is going to be a very small value, this is going to become large, or rather the learning rate for that weight is going to become large. When RT is large, the learning rate will become small. We are saying that for one of your weights, if your gradient was large, give it a small learning rate, and for one of your weights, if your gradient is small, then give it a larger learning rate. This seems to fit with the intuition that we had so far, and the nice part now is this kind of an approach, because RT is maintained for each gradient or each weight individually, this automatically takes care of changing the learning rate for each weight differently. Let's try to understand this from a simple example. So we do understand that when your error surface, these are contour plots, when your contour plots are spherical, things are easier, it's easier to converge. When your contour plots get elliptical is where your oscillations can occur. Another important property of elliptical contour plots is that there are certain dimensions where the change can be rapid, a certain dimensions where the change could be rather small, which is what elliptical basically means. So if you see this example here, which denotes, let's assume, the gradient and the corresponding y2 value, we are now saying here that if you look at one of these, let's look at the black, frequent and irrelevant, which simply states that all those values keep changing regularly, but they don't seem to be connected to the class output. Okay, these are some values and they don't seem to be connected to the class output in this particular scenario or the output of whatever function you're modeling. While there could be other values such as red and green which change only once a while. So you can see in 5T2, it doesn't matter here as to what these quantities are, and this is only an example. So when phi t2 is 1, we see that yt definitely becomes 1. When phi t2 becomes 1, yt definitely becomes 1. It doesn't matter when it's 0, but when it is 1, the output is definitely 1. Similarly for phi t3, you see that when it's 1, the output is definitely minus 1. So it looks like this particular parameter changes only once a while, but when it changes, it makes an impact on the final decision. So this is a scenario that says that even if the gradient is small, but if it happens only once a while, let's give more weight to changes in those directions, in those weights. And that's what this algorithm does. So here is the algorithm. So you aggregate the gradient, you update your gradient accumulation. So you initialize your gradient accumulation in a parameter called RT minus 1 is equal to 0. And you update your gradient accumulation to be RT is equal to RT minus 1 plus grad theta t square. You keep accumulating the square gradients, and then this is the formula. A small observation here, which is probably not clear from this algorithm, is this particular quantity on step 9 is an element-wise product. Right? So which means, remember in this case that while alpha was a scalar so far, RT is a vector, root RT will also be a vector. So this entire alpha now, alpha by delta plus root RT will become a vector. It's a vector of learning rates multiplied by a vector of gradients, element-wise multiplication. It's sometimes also called Hadamard product. The Hadamard product is nothing but element-wise multiplication. Remember, it's not like dot product. In a dot product, you take element-wise multiplication and then add them all up and get a scalar. In Hadamard product, you simply take element-wise multiplication and your output is still a vector. You don't add them all. Okay, that's the main difference. And this operation here in step 9 is actually a Hadamard product, element-wise multiplication between two vectors. There is one problem with the Adagrad method. Can you try to spot the problem? The problem is that this gradient accumulation term RT is a running sum that simply keeps accumulating over iterations, which means as you run more and more iterations, it will only keep increasing and get higher and higher and higher over time, which means this denominator is definitely going to get high over time for all the weights. In particular, there are some of the weights for which gradients keep occurring in every iteration where the denominator term can very quickly increase. This will lead to a lower learning rate for those dimensions in the weights, and learning may not happen along those directions. RMSProp, which was a method that came along the same time as Adagrad, proposed a slightly different approach to this problem and said, let RT be a convex combination of RT minus 1 and delta theta t whole square. What is a convex combination? Where you have rho times one term plus 1 minus rho times the other term. It's a linear combination where the two coefficients add up to 1. So rho RT plus 1, rho RT minus 1 plus 1 minus rho delta theta t whole square. This now ensures that because of the rho and 1 minus rho, the sum cannot keep exploding and is now controlled. Think about it for a while as to why, and you'll get why this will not allow you to explode. And now your theta t plus 1 and theta, this entire expression is exactly the same as Adagrad. Here is the algorithm for RMSProp with only that change in the step where you have now the running sum of the accumulated square gradients to be a convex combination monitored by a quantity called rho, which is known as the decay rate. The decay rate decides how much you want to consider the previous squared gradient while you get the current squared gradient. Okay, very similar to momentum, but in a different context. The most popular algorithm that is used for training neural networks today for adapting learning rates is known as ADAM or adaptive moments. Adaptive moments uses a simple intuition of combining ideas of RMSProp and momentum in a way. Let's see how that is done. While undergrad and RMSProp accumulate gradients or the squared gradients, Adam, while undergrad and RMSProp accumulate the squared gradients, Adam accumulates both the gradient and the squared gradients. ST accumulates the gradient, RT accumulates the squared gradient just like RMSProp. Why? You look at the final update equation here. The update says that theta t plus 1 is equal to theta minus alpha st by delta plus rho rt. I'll explain the tilde part in a moment, but let's first assume that there's no tilde. Let's just assume st and rt. So what is this doing? Alpha by delta plus root rt is exactly the same that we saw in RMSProp and undergrad. ST would have been the current gradient in undergrad and RMSProp, but now ST is the running sum of the gradient. And what is the running sum of the gradient? Momentum. Remember, momentum was what you use the previous gradient, so on and so forth, using momentum term. Rho 1 is the momentum coefficient for us in this particular context. That's why Adam can be looked at as a combination of RMSProp and momentum. Now coming to why is this tilde here, why not just ST and RT, is for a very simple reason of doing what is known as bias correction in the initial iterations. In the initial iterations, if rho 1 is set to a high value, which is what is typically done, rho 1 just like momentum, rho 1 could be set to something like 0.9 or something like that. In your initial step, RT minus 1 would be initialized to 0. That's where RT minus 1 will start. 1 minus rho 1 will make it a very small value because rho 1 is close to 1. So which means the gradients will not have any impact on ST in the initial iterations until they add up. So there may not be much training that happens in the initial iterations. So what do we do for that? We say let ST tilde be ST by 1 minus rho 1 power t. Similarly, RT tilde be RT by 1 minus rho 2 power t. What does this do? If rho 1 is 0.9, remember 1 minus 0.9 is 0.1. So ST by 0.1 will now increase it tenfold. So by whatever fold it was reduced here, it's now going to increase it by tenfold in the initial iteration. What happens in later iterations? We have t here. T is the number of the iteration that you're talking about. What happens here? Remember rho 1 is less than 1. It's chosen to be 0.9 or something like that. So rho 1 power t will keep reducing over the iterations. 0.9 into 0.9 is 0.81. Right? So it keeps, as long as you have a value less than 1, as you raise it to the power t, it's going to keep reducing, which means this quantity in the denominator will keep reducing over iterations, and this is not the quantity in the denominator. The rho 1 power t will keep reducing to 0, and 1 minus rho 1 power t will get closer to 1 over the iterations, which means after a few iterations, ST tilde will become ST, RT tilde will become RT. So the step of bias correction was only to handle the initial epochs where the gradient may not have a significant impact. This is your Adam algorithm. It's simply a summary of what we just said. These are the two steps. You update a first moment estimate, which is the gradient. Second moment estimate, which is the squared gradient. You maintain a running sum of both. Correct for biases and do your update. The key thing in the update is you do not have the gradient here because the gradient is subsumed into ST. That summarizes the various methods of improving gradient descent while training neural networks. So some of the issues that we saw are plateaus and flat regions, local minima and saddle points. Other issues that we will see as we go forward are vanishing and exploding gradients. As neural networks become deeper and deeper, the gradients that propagate from the last layer to the first layer can keep vanishing or exploding. That can cause what are known as cliffs in the error surface. We will see this a bit later. Other challenges that could happen is sheer ill conditioning of the matrix of weights or the loss functions or the gradients that you're dealing with. Please look at this link here to understand what this means. You could face a problem of inexact gradients. The gradients numerically may not be computed properly. For example, finding if a gradient is 0 is non-trivial because numerically attaining 0 while training is not possible. You have to ensure that you manage it in some way. But in general, numerical issues in gradients could also cause problems. There could be poor correspondence between local and global structure, which means you have a global error surface and you want to get to the global minimum, but the local region in which you are in may not really correspond with that global structure and you will be stuck with trying to handle the undulations in that local structure. Choosing learning rate and other hyperparameters like the momentum hyperparameter or the decay rate are also problems to deal with. To summarize, the error surface or cost surface in neural networks is often non-quadratic, non-convex, high-dimensional, potentially many minima and flat regions. There are no strong guarantees that the network will converge to a good solution. The convergence is swift, or that convergence occurs at all, but it works. This is an issue that's being investigated today, but it's fabulous that training neural networks with stochastic gradient descent works and is being used around the world in several applications. Here's your homework. Read up Deep Learning book chapter 8, at least the relevant sections in that, as well as you can also go through Stanford CS 231 and this particular lecture on SGD. A few questions for you to take away is how to know if you are in a local minima or any other critical point on the loss surface. I did mention a few times that finding that or finding the convergence criterion is not trivial. Let's ask that question for you to find before we answer. Why is training deep neural networks using gradient descent and mean square error a non-convex optimization problem? This is the first question that we started with this lecture with. This is something for you to ponder upon. And finally, if we assume a deep linear neural network, no activation functions at all, would using gradient descent and mean square error still be a non-convex optimization problem when you train deep neural networks? These are some questions to think about, and here are references.